For decades, electricity planning has operated in silos, reflecting a unidirectional power flow from centralized generation through transmission and distribution networks to end customers. This traditional approach was effective when power generation was centralized, demand patterns were predictable, and the grid operated primarily in one direction. However, the electricity industry is undergoing rapid transformation that fundamentally challenges these traditional planning paradigms. The challenges facing modern power systems are multifaceted and interconnected. Variable energy resources, particularly solar and wind, undermine the core assumption of dispatchable generation that has historically guided planning decisions. Simultaneously, accelerated and uncertain load growth from electrification, data centers, and new industrial demand strains both generation and grid infrastructure. The proliferation of distributed energy resources, DERs, has transformed power flows from unidirectional to bidirectional, as customers now both consume and produce electricity. These shifts occur against a backdrop of rapidly changing policies and regulations. Federal Energy Regulatory Commission Orders 1920, 2222, and 2023 represent significant regulatory changes aimed at addressing these challenges by motivating coordination between different planning areas. However, misalignment between policy changes and infrastructure development can create stranded assets, regulatory bottlenecks, and suboptimal investment decisions. The increasing adoption of inverter-based resources, IBRs, presents additional technical challenges. Unlike traditional synchronous generators, IBRs operate with power electronics that impact grid stability in new and unexpected ways, particularly in weak grid conditions. System strength assessments for IBR-rich regions and addressing adverse control interactions between IBRs require advanced modeling across historically siloed teams. Climate change further complicates planning by increasing the frequency and severity of natural disasters, posing new risks to energy infrastructure. Rising temperatures can increase peak electricity demand while simultaneously reducing generation and transmission capacity. More frequent and intense wildfires threaten power lines, high winds can lead to tower failures, and floods and droughts impact hydroelectric generation and grid reliability. If not carefully accounted for, reliance on historical generation profiles can misrepresent future resource availability, potentially leading to planning decisions that underestimate the need for additional transmission and generation capacity. Integrated planning represents a fundamental shift in how we approach power system planning. As defined by the Energy Systems Integration Group, integrated planning is a comprehensive energy system planning approach that coordinates across systems to develop affordable, reliable, and robust investment plans. Integrated planning coordinates across electricity generation, transmission, distribution, and customer loads and DERs, and may also consider interactions between the electricity system and other energy systems. This approach moves beyond traditional serial planning, where information flows sequentially from generation planning to transmission planning to distribution planning, with limited feedback loops. Instead, integrated planning fosters continual data exchange and iterative feedback across all planning areas, creating a more holistic understanding of the system and its needs. To understand integrated planning, it's helpful to examine the 4 dimensions of power system planning: scope, scale, horizon, and action. Scope determines the plan's focus and boundaries, specifying what is included and excluded. Scale determines the size of the plan implementation, reflecting whether the plan targets a specific area or takes a broader approach. Horizon defines the duration over which the plan is intended to be implemented, while action defines the decisions informed by the plan. Traditional power system planning is typically divided into 4 main areas: generation planning, transmission planning, distribution planning, and customer loads and resources planning. In most organizations, these teams continue to operate in relative isolation from one another, each with their own objectives, modeling domains, and decision-making processes. Generation planning encompasses the strategic planning and development of generation and storage assets to ensure an adequate, reliable, and least-cost electricity supply. Transmission planning focuses on high-voltage infrastructure for reliable power delivery and system stability. Distribution planning addresses medium and low-voltage infrastructure to serve customers and accommodate DERs. Customer loads and resources planning involves demand-side resources, customer programs, and DER integration. Each planning area utilizes different modeling domains and tools. Generation planners typically use capacity expansion models, CEMs, probabilistic resource adequacy assessments, and production cost models, PCMs. Transmission planners employ AC power flow, ACPF, AC optimal power flow, ACOP, transient stability, and electromagnetic transient, EMT, models. Distribution planners work with unbalanced AC power flow, UACPF, and protection coordination models. Customer planners focus on load forecasting, DR hosting capacity, and virtual power plant aggregation. The integrated planning framework emphasizes information exchange across 5 key interfaces: generation/transmission, transmission/distribution, distribution/customer loads and resources, generation/distribution, and generation/customer loads and resources. By facilitating communication and coordination across these interfaces, the framework enables more comprehensive and effective planning decisions. Implementing integrated planning can be approached through a walk-jog-run progression. The walk stage focuses on establishing foundational communication, trust, and shared understanding among stakeholders and planning teams. The jog stage involves aligning key inputs, outputs, and planning assumptions across different modeling domains and planning areas to create consistency and interoperability. The run stage executes fully integrated models that enable cross-planning area decision-making and optimization. The value of integrated planning manifests across multiple dimensions. Lower costs result from optimizing resource allocation and eliminating redundancies. Increased system resilience comes from planning with a comprehensive view of the energy system, strengthening its ability to withstand disruptions. Streamlined processes emerge from enabling coordination and consistent data sharing across planning areas. Data integrity improves through standardizing assumptions and shared datasets. Accurate benefit accounting avoids double-counting benefits while ensuring that the unique advantages of each planning area are effectively incorporated into system-wide strategies. Finally, integrated planning enables balancing competing objectives, allowing trade-off analysis among priorities such as maintaining grid reliability, ensuring grid resilience, and minimizing costs. The specific value delivered varies by interface. The generation/transmission interface identifies cost-effective resource locations and avoids transmission-constrained generation investments. The transmission/distribution interface reveals hidden constraints and defers costly transmission upgrades by leveraging DERs. The distribution/customer interface optimizes DR hosting capacity and quantifies the value of flexibility programs. The generation/distribution interface co-optimizes utility scale and distributed resources while improving DER visibility. The generation/customer interface accurately values DERs and resource planning and designs effective customer programs. To realize these benefits, organizations must address key concepts in integrated planning software. The current state of planning software is often siloed, with proprietary data formats that hinder information exchange. Integrated software concepts should focus on open data exchange using standardized formats like CIM and OpenGIS to facilitate sharing. Co-simulation capabilities should enable different models to run iteratively and exchange data. Modular architecture should allow planners to swap in different models or tools for specific tasks. Finally, scalable computation leveraging cloud computing can handle the complexity of integrated planning. Successful implementation of integrated planning requires more than just technical solutions, it demands organizational transformation. Leadership plays a critical role in driving this change by securing executive sponsorship, fostering cross-functional collaboration, breaking down traditional silos, and developing shared metrics for success. Organizations beginning their integrated planning journey should identify a specific, high-value problem to solve that demonstrates clear benefits. Starting with the walk stage of communication and trust building is essential before advancing to more complex integration efforts. Establishing a shared data repository provides a foundation for collaboration and ensures consistency across planning areas. As organizations progress through the walk-jog-run approach, they should invest in training and tools that support integrated planning workflows. This includes developing staff capabilities in cross-domain modeling and analysis, implementing software platforms that facilitate information exchange, and creating processes that encourage ongoing collaboration. The future of the grid is complex, interconnected, and bidirectional.
Traditional siloed planning is no longer sufficient to ensure a reliable, affordable, and resilient electricity system. Integrated planning represents the essential evolution, a practical framework for coordinating across all planning areas to make optimal investment decisions. By embracing integrated planning, the power sector can move toward a more resilient, efficient, and affordable future. This approach allows utilities, policymakers, regulators, and industry stakeholders to address the intersecting challenges of cost, resilience, sustainability, and customer engagement in a coordinated and comprehensive manner.